Suppose we have a function of two variables, and that's defined throughout a region in the xy plane, or the function's domain, and we have a point in this region with coordinates xp and yp that's also in the region, and u is a unit vector with a component in the x direction and a component in the y direction. So the base point and a direction vector define the line in the xy plane. Now if we parameterize the line using an arc length parameter s, then we can write the x coordinate of a point on the line as the x coordinate of the base point plus the arc length parameter, which gives the directed distance along that line, multiplied by the x component of the unit vector. And the equation in the y direction gives the y coordinate of a point on this line using the y coordinate of the base point plus the arc length parameter by the y component of the direction vector. So we can write the rate of change of the function with respect to the arc length parameter in the direction of the unit vector evaluated at point P. And this here is known as the directional derivative, which is also denoted d, or the derivative of the function f in the direction of u evaluated at point P. And this is defined as the limit as point Q approaches point P. So we take the limit as the arc length parameter tends to 0, and the difference quotient is the function evaluated at xp plus the arc length parameter by u1 and yp plus s by u2 minus the function at point P on the arc length parameter s. And similarly, the partial derivative of f with respect to x evaluated at P is the directional derivative in the x direction. So our unit vector will be I hat, and that's evaluated at point P. So in this case, the unit vector has no vertical component, so this term will be 0 in the definition, and therefore y will be held constant. And similarly for the partial derivative with respect to y, the unit vector will be the j vector in the y direction. So this function represents a surface in space. So the function evaluated at point P will evaluate at the z coordinate of a point on this surface. So this point has coordinates xp, yp, and zp. So essentially if we cut a plane out of this surface that's parallel to the unit vector and passes through point P, so the plane's parallel to the unit vector u hat, then the plane intersects this surface in a curve. So the rate of change of the function in the direction of u is the slope of the tangent to this curve at the point P. So essentially u hat and the unit vector in the z direction form a right-handed coordinate system. Given the line that passes through point P with coordinates xp and yp, and we parameterize this line using the arc length parameter s, and the line points in the direction of the unit vector with components u1 in the x direction and u2 in the y direction. So the equations parameterizing this line with the x coordinate of a point on the line given by the x coordinate of the base point plus the arc length parameter by the x component of the direction vector and we had the y coordinate as yp plus s by u2. So therefore the directional derivative, being the derivative of the function f with respect to the arc length parameter s along that line, so it's in the direction of the unit vector u, by the chain rule, is equal to the partial derivative of f with respect to x by the derivative of x with respect to the arc length parameter plus the partial of f with respect to y by the derivative of y with respect to s. So we can observe this derivative evaluates to u1, and the derivative of y with respect to s evaluates to u2. So if we define a gradient vector which operates on the function f as the partial of f with respect to x in the x direction plus the partial of f with respect to y in the j direction, then we recognize this equation as the dot product between the gradient of f and the unit vector. And if we're evaluating this derivative at point P, then the gradient of f is also evaluated at point P. So this is denoted by the upside down triangle symbol and also called grad f, the gradient of f, or del f. So for a function of two variables, x and y, being a differentiable function defined in an open region that contains point P, then the directional derivative is defined at every point in that region. Now let's make a bit of room here. So given the definition of the dot product, we can write the directional derivative, so in the direction of the unit vector, as the magnitude of the gradient vector by the magnitude of the unit vector, which is 1, by cosine of the angle between them. So in other words, when theta is equal to 0, so the gradient vector points in the same direction as the unit vector, being in the direction that we're evaluating the derivative, then the directional derivative is equal to the magnitude of the gradient vector. So the function increases most rapidly in the direction of the gradient vector at every point P in the domain of the function f. And if theta is equal to pi, then we see the directional derivative is equal to the negative of the magnitude of the gradient vector. So when we're taking a directional derivative in the direction that's anti-parallel to the gradient vector, the function decreases most rapidly in that direction. And where theta is equal to pi on 2, cosine pi on 2 is 0, and the directional derivative evaluates to 0. So in any direction that's orthogonal to the gradient vector, where the gradient vector is not 0, the function does not change. And let's illustrate this in a quick example. So we'll move this over here. So given a hyperbolic paraboloid defined by y squared minus 4x squared, and we want to evaluate the directional derivative at point P with coordinates of 1/2 and 1/2 in the domain of the function, and we want to evaluate this in the direction given by this unit vector being 1 on root 2 in the I direction plus 1 on root 2 in the j direction. So using this equation, we can evaluate the gradient. So the gradient vector is the partial of the function with respect to x. So we get minus 8x in the I direction. And the partial with respect to y gives 2y in the j direction. So evaluating the gradient at point P, we have minus 8 by a half, which is minus 4 in the I direction, and 2 by a half is 1 in the j direction. So our gradient vector points somewhere in this direction in the xy plane. So the directional derivative at point P is evaluated by taking the dot product between a gradient vector and a direction vector. So here we're finding the derivative in the direction of u, which points in this direction, being 45 degrees from the horizontal. So taking the dot product, we get minus 4 on root 2 plus 1 on root 2, which is minus 3 on root 2. So that's the slope of the tangent to the curve in the plane that's parallel to the direction vector u. So note that the partial of f with respect to x evaluated at point P is minus 8 by a half, or minus 4. So that's this curve over here that's in the plane parallel to the I vector, which is the slope of the tangent to the curve in the plane parallel to the xz plane. So the I vector points in this direction. So the directional derivative in both cases is negative because the angle between a gradient vector and these two direction vectors is obtuse. So therefore the function is decreasing in the direction of u and also I at point P, but is decreasing at a higher rate in the x direction as opposed to the u direction. So the surface is steeper in the I direction. Recall that a curve in the xy plane can be parametrized using the parameter t, and the position vector to a point on the curve as a function of t, so that's measured from the origin, is the x coordinate of the point in the I direction plus the y coordinate of the point in the y direction. So if a function of x and y has a constant value along a smooth curve defined by the following position vector using the parameter t, then this curve is a level curve of f, and therefore we can write f of x as a function of t and y as a function of t is equal to a constant. And differentiating both sides with respect to t, we can apply the chain rule on the left hand side. So we have the partial derivative of f with respect to x by dx dt plus the partial with respect to y by dy dt. And on the right hand side, differentiating a constant gives 0. So this is equivalent to the dot product between the gradient of f and the tangent vector being the derivative of the position vector with respect to t. So if t was time, then this is the velocity vector, which is also tangent to the curve. So this dot product evaluates to 0. So therefore at every point in a domain with coordinates xp and yp of a differentiable function of two variables, the gradient of f is normal to the level curve through this point. So for this hyperbolic paraboloid, z is y squared minus 4x squared. So if we set z equal to a constant, so we have planes that are parallel to the xy plane, cutting this surface at different values of z. So if c is greater than 0, then we get hyperbolas facing the y-axis, and if c is less than 0, then we'll get hyperbolas facing the x-axis. So this point here has an x and y coordinate of 1/2. So substituting in this equation, we get a z coordinate of minus 3/4. So it's below the xy plane. So this is a contour curve at z equals minus 3/4. And we plot the level curve corresponding to this contour curve in the xy plane. So given the gradient vector is normal to the level curve at all points along that curve, then we can use it to find an equation of the tangent line to the curve through this point. So we can take another point with coordinates x and y somewhere along that line, and recall the equation of the plane is the dot product between the normal to the plane and the vector formed by 2 points on the plane. So the normal to the plane is given by the gradient of the function. So we have the partial derivative of f with respect to x, and the partial derivative of f with respect to y. And we take the dot product between this normal vector and the tangent vector. So we have x minus x naught plus the partial of f with respect to y by y minus y naught. And that's equal to 0. So as an example, in this case, we have x naught being 1/2 and y naught is 1/2, and the partial of f with respect to x evaluated at point P is minus 8x, where x is 1/2, so we get minus 4. And the partial of f with respect to y at point P, where y is 1/2, gives 2y by 1/2, or 1. So the equation of this tangent line is minus 4 by x minus 1/2 plus y minus 1/2, which is equal to 0. So we can write this in the form of y is equal to 4x, and we have minus 4 by minus 1/2 is 4/2, minus 1/2 is 3/2, and subtracting it from both sides, we get minus 3/2. So the tangent line has a positive slope, which makes sense, and a y-intercept below the horizontal axis. If we have a differentiable function of 3 variables, being x, y, and z, and the unit vector in 3D space, which has an x component of u1, a y component of u2, and a z component of u3, the gradient of f is also extended to 3 space. So we have the partial derivative of f with respect to x in the x direction, plus the partial derivative with respect to y in the y direction, and we add a partial derivative in the z direction. So therefore the directional derivative, being the derivative of f in the direction of the unit vector, has the same form, which is equal to the dot product between a gradient of f and the direction vector u. So that can be written as the magnitude of the gradient of f by the magnitude of the unit vector, which is 1, by the cosine of the angle between the two vectors. So therefore the function increases most rapidly in the direction of the gradient, decreases most rapidly in the opposite direction to the gradient, and the directional derivative is 0 in any direction that's orthogonal to the gradient. And these are obtained by setting the value of theta, being the angle between the two vectors, to be 0 in the first case, pi in the second case, and pi on 2 in this third case, which is exactly the same as the case where we had a function of two variables. Given the following function of two variables, find the gradient at this point and sketch the level curve through this point. So the gradient is the partial of f with respect to x, which is 2xy, and evaluating this at the given point, we get 2 by minus 1 by 1, which is negative 2. And the partial derivative of f with respect to y is x squared, and evaluating this at the given point, we get minus 1 squared, or 1. So the gradient of f has an x component of negative 2 and a y component of 1. So at the point with coordinates minus 1 and 1, the gradient goes negative 2 in the x direction and 1 in the y direction. So it looks something like this. Now the level curve of the function is obtained by setting the function equal to a constant and substituting for x and y. We have minus 1 squared by 1, so c is equal to 1. And turning this equation around, we get y is 1 on x squared. So as x approaches 0 from the left hand side, y goes to infinity, and as x approaches infinity, y approaches 0. So the curve looks something like this. We're noting the level curve is normal to the gradient vector at any point. And on the other side, as x approaches 0 from the right hand side, y goes to infinity, and as x approaches infinity, y approaches 0. So the other side of the level curve looks something like this. Find the derivative of the function in the direction where the function increases and decreases most rapidly. So the function increases most rapidly in the direction of the gradient vector. So the gradient of the function is the partial with respect to x. So that gives y plus 2x in the x direction, plus the partial with respect to y, which gives 2y plus x in the j direction. So evaluating the gradient at the given point, we get y is minus 2 plus 2 by 2, which is 2 in the I direction, and 2 by negative 2 is minus 4, plus 2 is minus 2 in the j direction. So given the function increases most rapidly in the direction of the gradient vector, then we want a unit vector in the direction of the gradient vector. So the gradient vector has a magnitude of the square root of 2 squared plus negative 2 squared, which is root 8, or 2 root 2. So we have 2 on 2 root 2 is 1 on root 2 in the I direction, and minus 2 on 2 root 2 gives minus 1 on root 2 in the j direction. So the derivative of f in the direction of u is the dot product between a gradient vector and the direction vector. So that gives 2 by 1 on root 2, or 2 on root 2, minus 2 by minus 1 on root 2, which is plus 2 on root 2, which is 4 on root 2. And the function decreases most rapidly in the direction that's anti-parallel to the gradient vector. So that would be in the direction of this negated unit vector. And therefore taking the dot product between a gradient vector and this direction vector gives minus 2 on root 2, minus 2 on root 2, or minus 4 on root 2, being the directional derivative in the direction anti-parallel to the gradient vector. Find an equation for the tangent line to the level curve at the given point. So in this case, our function of two variables is x squared plus y squared. So therefore the level curve is defined as f of x and y is equal to a constant, in this case being 9. And recall the equation of the tangent line is the partial derivative with respect to x by x minus the x coordinate of the point on the tangent line plus the partial with respect to y by y minus the y coordinate of the point on a tangent line, and that's equal to 0. So the partial of f with respect to x is 2x, and the partial of the function with respect to y is 2y. And if we evaluate these at the given point, we get 2 root 3 and 2 root 6. So the equation of the tangent line becomes 2 root 3 by x minus root 3 plus 2 root 6 by y minus root 6. And that's equal to 0. And you can solve this equation for y to write the equation of the tangent line in terms of the slope and the y-intercept.